So, good morning, everybody. Thanks for joining us. This month we have Dr. Siyuan Wu from the University of Southampton joining us. Siyuan received his PhD from the Southern University of Science and Technology in Shenzhen, China in 2023. His PhD work focused on SAS's radio emissions based on Cassini data. He joined the University of Southampton in 2024, where he is now studying Earth's radio emissions. His research interests include radio emission, generation mechanisms, propagation, wave-particle interactions, and their connection to magnetospheric processes such as Aurora and substorms. So welcome, Siyuan. Thanks for joining us today. And when you're ready, feel free to take it away.
Okay, thanks for the invitation. And okay, I shall just start. Hello, everyone. So today's talk is about the Aurora kilometric radiation, which is basically a naturally generated radio component, the high frequency wave generated inside the magnetosphere. And we see this is a quite ubiquitous phenomenon. Can be observed at both Earth, Saturn, Jupiter, and the other like magnetized planets. So this talk is mainly about the Aurora kilometric radiation, and I'll focus on some recent work carried out in the UK since last year, and I should acknowledge all the contributions of my co-authors listed here. So I'll start with a brief introduction of this radio emission stuff. So basically, the planetary radio emission, the first radio emission was discovered back to this 1955 using some post-war ground-based antenna. And so at this time, Burke and Franklin, they used this radio antenna, observed some periodic emissions when the antenna is pointing toward Jupiter. And later they found this reappearance time, this period of this emission is exactly the rotation period of Jupiter. So they confirmed the origin of this radio signal is from Jupiter, so hence generated from Jupiter's magnetosphere. And after that, we have the satellite in space. So we have the space measurement of this radio signal. And then we've discovered this Aurora kilometric radiation. At the beginning, they call it terrestrial kilometric radiation, which is a similar radio signal generated from Earth's polar region. And later, since we have the Voyager flyby of Jupiter, for example, Saturn, Uranus, Neptune, we all found similar radio signals generated from their magnetosphere. So this is a quite ubiquitous phenomenon and been so far widely studied. And I'll show you some example here. For example, at Earth, for this first column, you could see this is a radio wave electric field spectrogram, which is basically Fourier transformed time series signal. The wave intensity as a function of UT time and frequency, and you could see this kind of like broadband wave features here. And we also have the other radio component. For example, what's shown here is called continuum radiation, which is believed to be generated in the vicinity of the plasmasphere. And here is the second column. I show a Cassini observation at Saturn. So basically, on this spectrogram, we could see many radio components. For example, we have the narrowband emission, which is we use NB to represent them, and we also have the Saturn kilometric radiations. We call it SKR, and for Aurora kilometric radiation at Earth, we call it AKR. And similarly, at Jupiter, we also have many radio components. For example, the decametric radiation, hectometric radiation, and kilometric radiation. So as you could see, some of them are quite similar, and but at different planets, we have like kind of special features there. So these are the main target we want to study. And so basically, for studying these radio emissions, we use one fundamental knowledge is the dispersion relation of the wave, which is mainly what we shown here is the dispersion relation derived from the cold magnetized plasma. And so we have several branches here. As you could see, we have Hwayser mode, we have the Z mode, and we have the RX mode and LO mode wave. And for radio emission, because generally the components are in free space mode as shown here is basically in X and O mode, which is we call them free space mode is because if you check here, these two modes only have lower cutoff frequency limit, which means basically they can propagate in space freely. While the Z mode and the Hwayser mode, you could see they have a lower cutoff and a higher cutoff here. So which means generally these two modes are trapped inside the magnetosphere or in a certain region. So for radio emission study, we mostly focus on these two free space mode, namely the RX branch and the LO mode emission. And so let's go back to the discovery of the Aurora kilometric radiation. It was first observed back to something around 1960s using a quite early satellite. And for example, in this paper, this Dunkel et al., 1970, they actually reported this high pass noise in the data, and they found a very strong relation between this emission and the AE index. But at that time, they don't know what's that. They just call it the signal high pass noise. And it was later until this Professor Dunker's paper, like back to 1974, he basically gave a comprehensive study of this signal using this IMP-8 satellite, and he gave its a name called terrestrial kilometric radiation. And as you could see here, many features has been analyzed here. As you could see, this figure gives you the E over CV ratio of this signal, which is close to 1, means this signal is an electromagnetic signal. And also they saw this 1 over R squared decay of the wave intensity as a function of radio distance, which means this emission was generated close to Earth. And they also show this net set preference of the wave distribution. Also in this within this magnetic meridian plane, which is a rho Z plane, and here is you could see this is the region corresponding to the plasmasphere, and the wave occurrence actually show a cutoff around the plasmasphere, suggesting they are propagated in this free space mode because they have a lower cutoff at the plasma frequency, which is depends on the electron density. And basically, we have many studies, like hundreds of papers being carried out for this Aurora kilometric radiation. I'll try to briefly introduce the history. And what's shown here in this figure is the wave distribution projected to this magnetic local time and magnetic latitude coordinate. And we could see basically the black area shows where we could see the wave most frequently, and basically this the AKR show this cone-shaped propagation, which is basically towards the higher latitude, and they have a cutoff or disappearance at the lower latitude equator region, which is corresponding to the plasmasphere. And here this figure shows the correlation between the wave power, the power flux of the wave, and the AE index, and you could see they show a quite wide correlation. And here in this figure, I show some early observations of the Voyager. So during the Voyager, during the lunchtime of the Voyager, so actually they have some measurement of aurora kilometric radiation. And here, what shows here is the radio wave polarization data, which is direct measurement of the radio wave polarization, shows both the sorry, Come on this. As you could see here, we have both black and white color, which gives you both right-hand polarized and left-hand polarized wave. And this is consistent with the theory that the AKR generated in the northern hemisphere and the southern hemisphere can possess different polarization feature, but they both can be the right-hand polarized wave in the magnetic reference frame. And since its discovery back to 1960s, we have many theory as this screenshot show here from another paper. Actually, we have many possible generation mechanisms proposed to explain why we have this Aurora kilometric radiation. And it was until this paper was a theory of the terrestrial kilometric radiation published back to 1979. And basically, in this paper, they proposed this theory called cyclotron maser instability, which is due to the cyclotron resonance between the electrons and the wave electric field can efficiently amplify the wave. And many features predicted by this theory are actually confirmed by the later observations. And now this cyclotron maser instability has been widely applied to the generation mechanism both at Earth, at Jupiter, at Saturn, and also some of the solar radio emissions. And also possible, like a lot of people trying to use this theory to search for the exoplanet radio emission. And here I show the fast observation inside the AKR source region. So basically here we could see the wave spectrogram. You could see the emission with its wave frequency extending below this white line. This white line is the local electron gyro frequency. And as I just mentioned, this emission was generated through the cyclotron resonance, so the wave frequency is close to the local electron gyro frequency in the source region. So this observation actually gave you the source crossing of the Aurora kilometric radiation, and you could see we have the for example, we have the particle observations here, which shows you the depletion of the low energy electrons, and we only have the higher energy electrons at several keV. And if we check the differential energy flux here, you could see this kind of monoenergetic or inverted V electron features. And basically, the electron distribution function shown here gives you the source electron distribution, which can provide the free energy of the wave growth. So basically, inside the AKR source region, we see this kind of, they call it horseshoe distribution. Basically, we see a loss count here, and in addition, we see this kind of shell type electron distribution, which is due to the adiabatic motion of the electrons and acceleration, field line acceleration of the electrons along the field line. And this is actually quite consistent with the electron distribution function observation in the Aurora region, which is with the field line mapped to the Aurora. And also, like the electron density measurement inside the AKR source region suggests the AKR source are distributed along the field line that is like embedded in this lower density region. As we just mentioned, that we have the low energy electron depletion inside the source region, which is consistent with this kind of aurora cavity. So basically, the AKR source are distributed within this Aurora cavity where the electron density is quite low. And also we have a lower electron plasma frequency over electron gyro frequency ratio inside this region, because this is the polar region and along the Aurora magnetic field line. So the FP ratio, the ratio between the FP and the FC is much lower. And also, if the previous study has compared this Aurora kilometric radiation and the Aurora, and although this quite earlier study is quite rough, but they definitely show the correlation when there's AKR emissions and the satellites always see the discrete aurora or the aurora forms. And here I show some more examples on this correlation, as reported in this paper. For example, in the Aurora image, you could see we have a faint transpolar Aurora arc features here. And during this time, the spacecraft, this could be the Vikings satellite, which is a Sweden satellite, and you could see the AKR emission here, and you see this kind of funnel shape on the spectrogram, and exactly at this deep point, if we show the local electron gyro frequency, we could see the similar feature at this point where the emission, the frequency can touch the local gyro frequency, gives suggests this is a source crossing, and exactly at this point, the spacecraft footprint. The footprint of the spacecraft trajectory projected onto this Aurora frame, you could see which is this sharp mark, and you could see basically it means that this radio signal was generated along the field line that mapped to this transpolar Aurora arc. And we could also use some like we call direction finding using the radio antenna on board the spacecraft, or using, for example, multi-spacecraft triangulation inversion method to use this radio wave spectrogram to invert the source distribution of this radio emission. And you could see here they have this is the polar UVI observation of the aurora, and during the same time you could see the radio emission, the source region of the radio emission are actually mapped to the aurora quite well. Suggests there is a strong correlation between this AKR and the aurora. And so because this signal was discovered back to like several decades ago, so basically we have hundreds of papers like focus on different aspects of this radio emission. So I tried to summarize all the features here. For example, the basic physics parameters of the AKR, like the frequency, wave mode polarization, and their power, and occurrence rate. For example, we have a strongest occurrence rate at the AKR at the night side, which is because AKR Aurora correlation, and also this AKR is strongly correlated with the substorm activity, as shown by the correlation between the wave power and the AE index. And also we have the generation mechanism attributed to the spectral maser instability, and the propagation, and also we have some magnetospheric implication. For example, the previous study shows very strong correlation between the AKR and the substorm activity, and the AKR between the aurora, between the AKR and the aurora transpolar arcs and possible other aurora forms. And we also have papers reporting AKRs related to, for example, the birthday bug flow in the magnetic region, field line current density, X-ray aurora, solar wind parameters, like lots of parameters. This kind of correlation has been done. So this is a rough introduction of the history of this AKR research. And so we could move to some recent works being carried out on this AKR. And since I started from last year, and I was trying to give a statistical study on this kilometric radiation first, by using multiple satellites, because so far we have many satellites like with a radio instrument, and the data are already there. Basically, I use wind waves data from 1994 to 2004, and the polar PWI data, which is around 1.5 years, and the RRC data, RRC PW plasma wave. Sorry, I forgot the full name of this instrument. And what's shown here is the spacecraft trajectory projected onto this magnetic meridian plane and the equatorial plane. So for wind, the spacecraft provides a quite large area, like the spatial coverage, from close to Earth to up to like 330 Earth radii. and both north and south we can reach a maximum to like 150 Earth radii. And for polar and Arazi, they mostly covers the inner magnetosphere region, like within 8 Earth radii, and they gave a quite uniform uh, magnetic local time coverage. And as you could see here, it's like this three spectrogram gives you three examples, like a 1 day observation with this AKR. But like different instruments gives you different time resolution here. First, we have this statistical distribution with the AKR, as you could see from large scale in this panel A to like we zoom in this occurrence rate to a smaller, finer spatial scale, like the grid size, and you could see immediately we could see a higher latitude occurrence preference here, especially here you could see. So it's generally we could see most frequently the AKR above like 30 degree in magnetic latitude, and there's a blocking area of this AKR at the equatorial plane corresponding to the plasmasphere. And also for the equatorial distribution of this wave, we have the very obvious night side preference for the wave occurrence. And you could see in the middle scale, we see this kind of spiral uh, distribution, spiral shaped distribution of the higher wave occurrence rate. And also, like if we further zoom in this view, we could see definitely the night side preference of this wave. And also we see another like a higher wave occurrence region above the polar region, which is this circle is like the radius equal to 1. So this is the Earth's shadow. So basically this is measured above the polar region, and we also see a higher occurrence rate there. If we separate the wave occurrence rate to different frequency to see this plasmasphere shadowing effect of the emission, and we could see here from panels A to D, we have the from lower frequency to higher frequency, and you could see although we have a higher occurrence rate of the wave at higher latitude, but within the equatorial plane, we still have some emissions being observed here. And if we uh, we try to explain this phenomenon, why we have this equatorial observation of the emission, because we know here is the plasmasphere, they should block all the emission, and as predicted by the theory, as you could see here in this right hand figure, because theoretically this is a ray tracing simulation of the AKR emissions propagation, and you could see we have plasmasphere here. And so theoretically, if we have a plasmasphere here, you have something blocked the propagation of all the emissions to the equatorial region. So you will have a almost empty observation of the wave here. But if we compare the observation, it's definitely we see although we see a rare AKR emission here, but we still have a lot of them being observed in this shadowing region. And to explain this, we checked some observation of the AKR near the plasmasphere, as I show you here. You could see all these observation examples. The Aurora satellite was around the plasmasphere, and you could see sometimes we see this kind of modulated AKR emission, these kind of vertical straps. And if you check on the spectrogram, we have these lines, line emissions here. This line emissions is a local upper hybrid emission, which is basically here is proportional to the local electron density. And so you could see the, it seems this vertical strapped emissions are corresponding to these dips inside this, as you could see from this line emission, which is actually corresponding to the local electron density minimum. So, which means actually we have some emissions are locally trapped in this low density region due to the lower electron plasma density, and sometimes you could see here is quite obvious for these dips along the local upper Hubble frequency, which gives you the local electron density depletion, and we see this enhanced wave intensity inside them, and this is quite interesting features. And we also see actually below this, if you could see here in this panel D, we also have a lower frequency emissions that also tend to be modulated by this lower electron density region. These are Whistler mode emissions actually. And so this is reminiscent of some, for example, the so-called ducted propagation of the Whistler mode emission. And we believe also for this AKR emission, which is another mode like the RX mode emission, can also be ducted. And what we do here, we do another ray tracing simulation by incorporating some low density field line structures inside the plasmasphere. And then we do the ray tracing again. And as you could see here, we launch the rays, and immediately we see that a lot of rays being ducted or trapped inside this low density field line structure. They can propagate from one hemisphere even to the opposite hemisphere. And when the wave incident angle to this low density flux tubes, when this incident angle is appropriate, they can be leaked to the equatorial plane. And basically, this can explain why we see the AKR emission inside this shadowing region. And so we found this feature could be very important for the AKR propagation. So here's all the content for the AKR statistics. We find some new features of this ducted propagation of AKR. And then during the processing this polar data, we noticed that there's a lot of source crossing event in the data. As I just mentioned in the introduction section, this emission was generated due to the cyclotron resonance between the wave electric field and the electron. So when the spacecraft observed the wave emissions close to the electron gyro frequency, which is this white line here, it means that point gives you the source crossing with our kilometric radiation. So we searched the whole polar data set to find all these um, source crossing point. And you could see some examples shown here. For example, here the white squares give you the source detection, which the wave frequency is touching this local electron gyro frequency. And if we check the electron particle observation, this is differential energy flux, and you could see basically this is Aurora oval crossing, and we see the enhanced particle flux here. And if we zoom in this time interval, we can see here, basically during the source crossing, we see this kind of monoenergetic electron features, and also possibly the broadband electron precipitation. And also for a second example here, this is dominant by the broadband electron precipitation. And in total, we found like 18,000 source crossings using the entire polar data set. And we could get some parameters here. For example, the electron plasma frequency, the FP frequency at the source is mostly below 20 kHz, which means the electron density is quite low inside the source region, consistent with the previous observation and the theory. All the source crossing AKR frequency is around 200 kHz, and we have this ratio between the FP and FC is below 0.1, which is also consistent with the theory. We also have the superposed epoch analysis of the electron spectra during the AKR source crossing. So we subtract all these electron spectra and simply superpose them together, and we see systematically we have a bump on tail at the higher energy, which could provide the free energy of the wave growth. And if we project all the footprint of the source crossing of the AKR onto this magnetic polar coordinate, and we could compare this AKR source distribution with Aurora as shown here. You could see this is the polar UVI observation of the Aurora, and this is the AKR source footprint. And immediately we see this kind of like really nice correlation between the AKR and the Aurora. And this is so far the first, I wouldn't say the first, but the most complete picture of the AKR source distribution. As you could see in this previous work, they could only show you some average of a certain time period uh, 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 source calculation using some like very good data because they ask the signal noise ratio to exceeding certain threshold or something. And what's shown here in this panel D, this panel B gives you the spacecraft trajectory showing the quite uniform distribution of the footprint of the spacecraft, and panel D gives you the intensity during source crossing. So although we both have the AKR source distributed at night side and day side, but the day side AKR source generally are quite weak if compared to the night side. And because we have like 18,000 source crossings, so we have many interesting source crossing features. For example, here you could see this is the wave spectrum where the AKR frequency touched the local electron gyre frequency, and we see quite faint emission here. And if you check the electron feature here during the same time period, the electrons are generally below 1 keV, which is contradictory with the previous understanding that generally they saw AKR source electrons above 1 keV at several keV. And so this is quite interesting. And if we compare the simultaneous Aurora observation here, as you could see, so during this time period, the AKR source along the footprint was marked as this orange marker. And so this two pink marker gives you the closest time of this Aurora image has been taken. And you could see when AKR cross this very strong AKR source with like higher energy electrons, actually this position actually corresponding to the very bright Aurora arc here. But for this faint AKR source region with lower electron energy precipitation is something around the poleward region of this bright Aurora arc. And also here we have another example. Like for this, at the beginning we have a quite weak AKR source crossing, and if we check the electron features, we see this kind of higher energy precipitation above 1 keV, but with lower electron flux, which could be corresponding to the diffuse aurora feature. And if you check the position of the footprint, there something around this point is at the equatorial edge of this bright aurora arc, which could be indeed corresponding to the diffuse aurora, which generally is observed at the equatorial edge of the bright aurora arc. And also corresponding to this very strong spot AKR source, we have this kind of enhanced electron flux here, and the footprint is corresponding to this bright aurora arc. So we show this like almost like one-to-one correspondence between the AKR and the Aurora, and we see like different electron precipitation features. So using this almost like 18,000 radio emission source crossing, we could do a clustering or like categorizing of all the source electron spectra. For example, we could simply categorize them to four types. One is, for example, this type A is like takes 31%, almost 32% of the whole 18,000 electron spectrum, which gives you this kind of broadband energy peak at higher energy with an average electron energy at 1.3 keV. And we also, the second type, we have a little bit like mono-energetic energy peak at the higher energy. And we also have this a little bit broadband, but with a peak at lower energy below 1 keV. So this kind of electron type. We also have this diffuse type, which gives you still a high energy peak above 1 keV, but lower energy flux here. So corresponding to the diffuse type electron precipitation, corresponding to the diffuse aurora. So this was the first time we categorized possibly the source electron precipitation type, and which can be contributing to the generation of the AKR. We also show the so different types. We have the different types of AKR radio oval, which is a source radio oval here, as you could see. So for the broadband type, we have this kind of quite wide source distribution. For the monoenergetic type, we have this AKR source more confined to the night side section. And for the low energy part, especially for the day side, we have this kind of a lot of AKR source corresponding to this low energy electron precipitation. And the diffuse type precipitation takes like the least part is like around 2%, and all the source distribution along the equatorial edge of this aurora oval. And generally, for the first two types, which is the broadband type, type A, and the monoenergetic type, type B, we have the strongest AKR intensity being generated. And for the this low energy precipitation and the diffuse type, we have the weaker AKR intensity if compared to the first two types. And so this leads to the final picture of this figure, the right-hand side figure. So generally, we have the AKR emission is excited above the optical aurora along the B field lines. And since the wave frequency is close to the local electron gyro frequency, which is proportional to the local magnetic field strength, so we have basically higher AKR generated at the bottom along this field line, but still above the optical aurora. And so towards the higher altitude, we have a lower AKR, lower frequency AKR being excited, and they can exactly, the footprint along the B field can exactly map to the optical aurora as shown here. And so after we get all these understanding of the AKR statistic, propagation, and their generation mechanism, we turn to, sorry, I may take more time for this, and we turn to this correlation between the AKR and the substorm, since many studies has shown that AKR has a very strong correlation to the AE index, to the substorm onset, to this to a lot of this kind of geomagnetic activities, as you could get from the previous paper. And we check here. First is some aurora feature to give you some expression of the aurora observation near the substorm onset. For example, here we show this kind of periodic aurora spot here, which generally they call it aurora beads, and this kind of feature are believed to be exactly observed prior to the substorm onset. And sometimes actually we see a several group of this kind of aurora beads. For example, here shown here, you see first we have a periodic stop spots aurora beads here, and this didn't lead to a full the later expansion of the aurora. As you could see in this this wave-like arc or aurora beads, they just faint somehow here. And we see another group of aurora also with kind of wave-like features or aurora beads features here, and later they lead to the expansion of the aurora. So maybe first this group could be called a pseudo breakup or pseudo storm, and this aurora feature could corresponding to the aurora beads. And if we check the AKR near the substorm onset, as shown here, I show you 5 examples. We could see basically exactly at the substorm onset, we see the enhancement of the AKR across a very wide band in frequency, and also the enhancement in intensity. And you could see here is all the substorm onset. But exactly before the substorm onset, we see this quite faint frequency drifting features of the AKR with its finer structures. They either like we see a sudden appearance of this emission on the spectrogram, or it's like emergence from a background as shown here. And sometimes we see several groups of these frequency drifting features exactly before the substorm onset. And this is quite similar to the first case in the Aurora I show here. This first we have a group of this AKR, like these frequency drifting structures, but didn't lead to full substorm. But later we see another group of these frequency drifting features lead to substorm onset. And so this possibly it's just quite like interesting. We could speculate that these finer AKR emissions could be co-generated with the RRBs. And so here we find some simultaneous observation, as you could see in this two example. The first one here is to make it like easier to do the comparison. So I plot this spectrogram vertically. So here, the vertical axis you have the UT time, and this is the frequency, and this is the kilogram of Aurora with the original Aurora images shown here. And you could see, so at the beginning in this panel C, you could see it's like from a quite quiet background, and suddenly we have this a wave-like Aurora arc moving into the field of view, and they gradually enhanced, and finally they have this expansion feature lead to the full substorm. And if we check the kilogram of this event, you could see this faint arc moving into the field of view. And during the same time, if we check the radio data, this AKR also see this kind of, you see this finer frequency drifting tones here with up and down frequency drifting feature. This is exactly corresponding to this arc prior to the substorm onset, and exactly at the onset we see this low frequency tension and enhancement in the intensity. So this suggests this radio emission can really being co-generated with this Aurora feature prior to the substorm onset. And here, like in these panels, we just show do some geometry calculation to show that the satellite can really receive the radio signal connected to this Aurora arc, and the observation. The calculation suggests that indeed, like this is the camera's field view, and this contour map gives you the radio visibility area of the Aurora spacecraft. So it's suggesting spacecraft can receive the radio signal generated above this Aurora feature. And here I show another example. And you could see here, exactly before the substorm onset, we have this RRBs, this kind of periodic spot here, and we have the enhancement or the frequency drifting features on the AKR spectrogram. So suggesting basically we have this AKR features can be a radio counterpart of the RRBs. And we also do a statistical examination of these features. For example, for the duration of this AKR precursor feature and the RRBs, we see for regular substorm, their duration is something around 2 minutes before the substorm onset. And sometimes we also have these features corresponding to the pseudostorm or pseudo breakup, and the duration is a bit longer. But the distribution should quite consistent between the AKR and the Aurora feature. And we also calculate some other characteristics. For example, because we have the frequency drifting features of this signal, and we could actually calculate the frequency and the altitude of AKR source region. So generally, all these precursors are observed at something around above 200 kHz, and with their source altitude distributed around 5,000 kilometers above Earth. And their duration for one frequency drifting time, for example, as you can see here, for one frequency drifting features, the duration is something around 1 minute. And so since this is the frequency drifting features can corresponding to the movement of the AKR source, and so the movement, the distance of this movement of the AKR radio source is something around 1,000 kilometers during this 1 minute duration. And we also have the frequency drifting rate for example, the DFDT, the frequency variation of this feature, which is around several kHz per second. And this several kilohertz per second as shown here by this blue histogram, and the converted velocity of this frequency drifting range is around 10 kHz, 10 kilometers per second, and this match the local, for example, these two shaded region are the proton acoustic velocity and oxygen acoustic velocity. So this basically this moving velocity is corresponding to the acoustic, the proton acoustic velocity in the AKR source region. And also we have the period, because you could see here sometimes these frequency drifting features show this periodic manner. And this period is something is around several tens of seconds within 1 minute. And this is actually quite consistent with the previous published Aurora B's period, as you could see here. And so finally, we draw this final picture of the story, which is basically because the Aurora beams was shown to generated by the kinetic Arfan wave, which could be generated due to some, for example, ballooning instability in the middle magnetosphere. And so we just adapted this mechanism to explain our observation. So first, inside the magnetosphere, we have this kinetic Arfan wave generated, and they could excited the what we call the double layers inside the around the AKR source region along the B field line. Because the double layer electric potential structure can moving along the B field at the local ion acoustic velocity, which is consistent with the AKR source drifting speed. So we are proposing that, okay, this kinetic Arfan wave can excite this double layer along the B field line. And inside this double layer feature, we have the AKR generated, and because the double layer was moving at the local acoustic speed, and so we have the frequency drifting rate is corresponding to the local ion acoustic speed. And also because this is generated by the kinetic Arfan wave, so naturally we have this periodic manner in this radio emission, similar to the Aurora B's period. And so this is the whole picture we draw from this AKR observation. And so this we came to the conclusion part. So first part, we have a new statistic picture of the AKR using like 3 spacecraft from wind, polar, and RRC data, and we found a consistent distribution of the AKR distribution. For example, the night side preference, high latitude preference of the wave occurrence. We found the ducted propagation of the AKR, and this was validated by the ray tracing simulation. We also found the many new AKR source crossing events indicating different types of electron precipitation can both contribute to the generation of AKR. Finally, we observed these AKR precursors exactly before the substorm onset, indicating actually we could use this radio emission to diagnose the substorm onset dynamics. So basically, that's all the content. Thank you.